In the previous module we calculated the distances and magnifications for plane flat mirrors and plane transparent materials. In this module we will tackle problems related to materials having curved surfaces. Here we have a simulation of convex mirrors. Convex mirrors have the reflective surface on the outside facing the object. This object creates an image that is observed in the simulation. As you change the height and position of the object, the image also changes. Let us look at some of the rays that are present during reflection. First we have the parallel ray shown on the figure. The parallel rays are drawn parallel to the optical axis. After reflection, this ray passes through the focal point F of the convex mirror. Here we draw a dashed line to indicate that it is in the imaginary space in the mirror space or imaginary space. Here we see that the dashed line starts from a position where the parallel ray hits the surface of the mirror and then goes towards the focal point of the mirror. The direction of the reflected ray is based on the dashed line where we see that it has the same orientation but it is pointed outwards of the curved mirror surface. The focal ray is drawn proceeding toward the focal point and it is reflected parallel to the optical axis. As we see, we have two dashed lines here. The first is the lighter dashed line where it is oriented in the same direction as the focal ray. This light dashed line hits the curved surface and it indicates the intersection of the focal ray and the curved mirror where the parallel lines will emerge. The solid dark line or simply black line indicates the parallel orientation of the reflected ray. So it is parallel to the optical axis and it is pointed outwards as shown in the image. Radial ray is drawn towards the center of curvature C perpendicular to the surface and it is then reflected back to its original path. Here we see the dashed line has the same orientation as the radial ray and it intersects the center of curvature. The ray simply returns back to its original path in the opposite direction as the original ray. The central ray is drawn towards the vertex and it is reflected with an equal angle measured from the optical axis. Here we see the ray hits the vertex and forms an angle theta A. The reflected ray originates at the vertex and it is tilted by the same amount of angle as its initial ray, which is angle theta A. Both angles are measured from the optical axis. To determine the position of the image, we locate the intersection of all the rays and we see here that it is on the right side. Due to the physical limits of a convex mirror having its reflective surface diverging from all the outgoing light, the images that it can produce for objects that are in front of it are only virtual images. We then establish the sign convention for curved mirrors. The object distance S is positive since it is on the same side as the incoming light. This object is considered as a real object. The image distance S' is negative since it is on the opposite side as the outgoing light. This image is considered as a virtual image. Convex mirrors and plane mirrors can only create virtual images. The radius of curvature here is negative since the center of curvature is on the opposite side as the outgoing light. The relationship of the distances S and S' is given by equation 1. Here we see that it is the sum of the ratio of the distances S and S' which is proportional to the inverse of the radius or focal length. For its magnification it is given by equation 2. Magnification can be expressed as the ratio of the distances or the height of the object and image. For plane mirrors the magnification would result in 1 since they are expected to have equal height or equal distances. Here we have a sample problem about convex mirrors. A 4 cm tall light bulb is placed a distance of 35.5 cm from a convex mirror having a focal length of -12.2 cm. Determine the image distance and the image size. First we draw the problem. Here the bulb is represented by an arrow. We add arrows to graphically determine a rough position of the image formed. Here we use the parallel ray, focal ray, and central ray to determine the position of the image. We see that the image is on the right side of the mirror and appears to be a virtual type of image since it is on the opposite side as the outgoing light. To determine the distance of the virtual image and the height of the image we use equations 1 and 2 designed for curved mirrors. Rewriting equations 1 and 2 to solve for the image distance and height. We have that the distance of the image S' is equal to -9.08 cm, which agrees with the graphical representation as indicated by the negative sign. For the height we have that it is about 1.02 cm and also agrees graphically with the image. The positive sign of the height indicates that it has the same orientation as the real object here, which is in an upright orientation. Here we have a simulation of a concave mirror. As we move the position of the object we are able to produce images that are on the same side or opposite side of the object. Let us look at some of the rays that are present during reflection. First we have the parallel ray shown on the figure. The parallel rays are drawn parallel to the optical axis. After reflection, this ray passes through the focal point F of the concave mirror. The focal ray is drawn proceeding toward the focal point and it is reflected parallel to the optical axis. Radial ray is drawn towards the center of curvature C perpendicular to the surface and it is then reflected back to its original path. Shown by the small inset at the upper right, the ray would hit first the surface of the concave mirror before it is reflected back to its original path. The central ray is drawn towards the vertex and it is reflected with an equal angle measured from the optical axis. The nature of its angles is still the same as the convex mirrors where they are equal and measured from the optical axis. Image position is determined graphically by the intersection of all rays. Here we see that it is on the same side as the outgoing rays, which makes the image a real image. Unlike convex and plane mirrors, concave is capable of producing both real and imaginary images. The object distance S is positive here because it is on the same side as the incoming light. This object is considered a real object. The image distance S' is positive here because it is on the same side as the outgoing light. The radius of curvature for the concave mirror is positive because it is on the same side as the outgoing light. The formula for the relationship of the S and S' and the magnification is given by the same equation with the convex mirrors, which are equation 1 and 2. Here we have a sample problem on concave mirrors. A luminous object is 4 meters from a wall. So this image is a real image since it can be projected onto a screen, and for this case it is a wall. You are to use a concave mirror to project an image of the object on the wall, with the image 2.25 times the size of the object. How far should the mirror be from the wall? What should its radius of curvature be? You can see from the picture here that the object must be between the wall and the thin concave mirror for the image to be real and projected onto a wall. For letter A. To find the distance between the mirror and the wall, we determine the value of distance of the image S'. We use equation 2 or the magnification. Rewrite this and we get equation B. Substituting equation A, we see that the distance of the real image, which is also the distance between the mirror and wall, is 7.2 meters. A positive value shows mathematically that it is on the same side as the outgoing light and it is a real image. From this we can calculate the real object distance also using equation A. Substituting the value of S', we get that the real object distance from the mirror is 3.2 meters. For letter B, to determine the radius of curvature we use equation 1. Rewriting this to solve for the radius R, we see that it is about 4.43 meters. The positive sign of the radius R shows mathematically that the center of curvature is on the same side as the outgoing light. The difference between real and virtual images. An image is considered real when it is on the same side as the outgoing light. An image is considered virtual when it is on the opposite side with the outgoing light. Real images can be projected onto a screen, but virtual images cannot be projected onto a screen. Here we have a convex mirror and its image is a virtual image. Since it is a virtual image, then it cannot be projected onto a screen. We are familiar with the term called magnification, and it is technically defined as the ratio of the heights of the objects and image. It is also known as lateral magnification. Here we have an image of an animal, and when we increase its magnification we can see more and more detail. Here we have an image of a fly and we examine it visually with specialized microscopes using electron beams rather than visible light. As we increase the magnification we see more and more details of the compound eyes of a fly. Here we have a summary for the type of images that can be produced by different mirrors. The plane mirrors have an infinite value of its focal length, which approximately results in a plane flat mirror. The distances S and S' are equal but in opposite directions as indicated here. For the concave mirror it has a positive focal length by the nature of its relationship with the outgoing light, which is that they are on the same side. Here we see it has real and virtual images. This depends on the position of the object. So if it is positioned twice greater than its focal length but it is greater than its focal length, the image formed will be real. But if the object is less than its focal length, the image formed will be virtual. Then we have the convex mirrors where its focal length is of negative value since it is positioned on the opposite side as the outgoing rays. Its orientation and magnification will also change based on its position with respect to the type of mirror. That is it for now, and I hope you learned something new today. For questions and comments you may send them to diyeslearningstuff@gmail.com. You may review the slide on YouTube at Diyes Learning Stuff. Note, please do not forget to use your school email. Also write your complete name and class section. Thank you for listening and see you next module.